Introduction. Heat capacity is the ratio of the heat absorbed by the material to the temperature change. It is usually expressed as the calorie per degree in terms of the actual amount of material being considered, most commonly a mole. The heat capacity in calorie per gram is called specific heat capacity. The definition of the calorie is based on the specific heat of water, defined as the 1 calorie per degree Celsius. The objective of this experiment is to estimate the heat capacity of different metal provided and to estimate the entropy generated when these metals are dropped in the container containing water. The scope of this experiment is to compare the heat transfer property of copper, aluminium, and iron, record the temperature changes in the second beaker every 20 seconds until 3 consecutive readings are constant, and calculate the specific heat capacity of each metal based on the temperature changes observed.
A body's heat capacity is the amount of heat necessary to rise its temperature by 1 degree Celsius. When two bodies of differing temperatures exchange heat, the amount of heat lost by the warmer body equals the amount of heat absorbed by the cooler body, and an intermediate equilibrium temperature is attained. This is true as long as no heat is lost to the environment. A heated material of non-mass m and temperature is dropped into a calorimeter containing non-mass m2 of cold water in this experiment. After that, the equilibrium temperature is determined. The amount of heat lost by the solid must be the same as the amount of heat gained by the water. Heat lost by the solid equal to m times Cp times the change of the temperature of solid. The second one is the heat gained by water equals to m2 times Cp times the change of the temperature of water. A system or its surroundings entropy change can be negative, but total entropy generation is positive. The increase of entropy principle, Sg more than zero, requires that a process operate in the direction of S generation more than zero. The magnitudes of the irreversibilities present during the process are measured by the entropy generation. The entropy produced during this process is determined from S equals to m times Cp times ln T2 over T1. Total S equals to S metal plus S water. The mass of water in kilograms kg can be obtained using the equation below. Mass of water in kg equals to volume of water in ml times 0.001 kg over 1 ml. The specific heat capacity of water is given as 4.187 kJ per kg times K in this experiment. The value of specific heat capacity of water will be used as a constant throughout the calculation for each type of metal.
For the apparatus, we use thermometers, heater, water container, three types of metal, which is copper, aluminum, and iron, weighing scale, stopwatch, and aluminum foil. Next is figure 1, which shows the experimental apparatus for the experiment, and figure 2 is the recording the temperature every 20 seconds until 3 constant values of temperature.
Methodology. The copper metal block was weighted by using the weighting scale. The weight of the copper block is recorded in table 1. The 90 ml of water was filled into the 100 ml of beaker. The beaker with the 90 ml of water was heated by using the hot plate. The copper block was attached to a metal spring. The copper block which was attached to metal spring was put into the heated water until the copper block was fully submerged into the water. The copper block in the water was heated until the water in the beaker reached 80 degrees Celsius of the temperature. The temperature of the copper block was assumed to be equal to the temperature of water. A second beaker was prepared and the 90 ml of water was poured into the second beaker. The initial temperature of the water in the second beaker was measured by using a thermometer. The initial temperature of the water was recorded in table 1. When the water in the first beaker reached 80 degrees Celsius, the copper block which attached to the metal spring was taken out from the first beaker. The copper block which was attached to the metal spring was immediately transferred to the second beaker that contained a 90 ml of water. An aluminium foil covered the second beaker to minimize the heat loss to the surrounding. The temperature of the water in the second beaker was recorded in every 20 seconds until 3 constant value of temperature in table 1. The water in the second beaker was changed throughout the temperature recording process to ensure the even heat distribution. Step 1 to 10 was repeated by replacing copper metal block with aluminium and iron metal block.
This is the data that we obtained from the experiment for each metal for copper, aluminum, and iron.
In this experiment, the volume of water used for each type of metal was kept constant as 90 ml. The mass of water in kilograms can be obtained using the equation below. Mass of water in kg equals to volume of water in ml times 0.001 kg over 1 ml. The specific heat capacity of water is given 4.187 kJ per kg times K in this experiment. The value of specific heat capacity of water will be used as a constant throughout the calculation for each type of metal. For the calculation sample for results, which is copper, the mass of water is equal to 0.09 kg. The specific heat capacity of water is equal to 4.187 kJ per kg times K. The mass of the copper is equal to 0.1202 kg. The initial temperature of copper, which is T1, is equal to 70 degrees Celsius, which is equals to 343.15 Kelvin. The final temperature of copper, T2, is equal to 37 degrees Celsius, which is equal to 310.15 Kelvin. For water, the T1 is equals to 31 degrees Celsius, which is equal to 304.15 Kelvin. The T2 is equal to 33 degrees Celsius, equals to 310.15 Kelvin. Heat gained by the water equals to heat lost by copper. After we apply the formula below, we will get the heat capacity of copper is equal to 0.43745 kilojoule per kg times K. After we get the Cp copper, we will apply it into the S copper formula, which is M copper times Cp copper times non-T2 copper over T1 copper. After the calculation, we will get the S copper is equal to negative 0.00683 kilojoule per Kelvin. We will apply the same formula in the water, but use different the value of Cp, which is 4.187, and we will get the S water equals to 0.00736 kilojoule per Kelvin. So for the S total, we will sum it out, which is S copper plus S water. At the end, we will get the S total is equals to 0.00053 kilojoule per Kelvin. The table below shows that the result of calculation for each type of metal, which is aluminium, iron, and copper, just now. So we will get the S gent equals to 0.00015 for aluminium, 0.00022 for iron, and 0.00043 for copper. Next, we will calculate the percentage error for each type of metal. Percentage error equals to modulus experimental value minus the theoretical value over theoretical values time 100%. So for the copper, we get the 13.6 percentage. Table 3 below shows that the percentage error for each type of metal, which is copper, aluminium, and iron, for the copper is equals to 13.6%. Aluminium is equals to 53.2%. Iron is equals to 50.3%. The bar chart below shows that the theoretical value and experimental value of Cp for each type of metal. According to the engineeringmindset.com, the theoretical value of Cp for copper, aluminium, and iron are 0.385, 0.887, and 0.462 kilojoule per kg times Kelvin respectively. The table 3 and chart 1 shows that the difference between the theoretical and experimental value of Cp for each type of metal. The percentage error in table 3 and chart 1 shows that the percentage error for the value of Cp obtained for copper, aluminium, and iron are all above 10%. This indicates that the experimental value of Cp obtained for copper, aluminium, and iron is not so accurate. The total entropy generated by the heat transfer for copper, aluminium, and iron blocked to the water in this experiment is 0.00053, 0.00018, and 0.00027 kilojoule per Kelvin respectively. The positive value of the total entropy generated for these three metals indicate that the process of heat transfer from the metal block to the water is an irreversible process, which is also known as a real process that can occur in real life. The value of entropy change of metal, which is copper, aluminium, and iron, are all negative because during the process of metal transferring heat to the water, the metal undergoes exothermic process. The negative sign shows that this exothermic process causes an increment in the entropy of the surrounding, which is water. Hence, the entropy change of water for copper, aluminium, and iron are all negative value. Are all positive value. There are some sources of error that occurs to the inaccuracy of the experimental data. Firstly, the metal blocks have rust on them. The impurities of metal contribute the result obtained in the experiment are not the data obtained for pure metal. Secondly, the disturbance from environment where the experiment is conducted. The airflow from fan and windows cause heat loss from the second beaker when heated metal is in it due to the fan is not switched off and the water is open. The parallax error occurs when reading the temperature from the thermometer causes the inaccuracy of data of temperature. The metal blocks can be cleaned by using sandpaper to clean the rust on the metal blocks to minimize the presence of impurities in the metal blocks. We also can switch off the fan and close the window before conducting the experiment to avoid heat loss through combustion. To avoid parallax error, the observer's eye level is perpendicular to the scale reading of the thermometer. The importance of stirring the water in the container is to evenly distribute the heat in water. The temperature of the water at any point will be consistent in the container. The importance of transferring the hot metal quickly into the water in the second beaker because the heat from the heated metal block will lose through convection and radiation process during transferring into the water. This process of transferring the heated metal block from first beaker to second beaker as fast as possible to ensure that the metal block is still at initial temperature, which is 80 degrees Celsius.
In conclusion, as we measure the heat capacities of copper, aluminum, and iron, we calculated the entropy generated when these metals were placed in water. The specific heat capacities we found were 0.437 kJ per kilogram Kelvin for copper, 0.415 kJ per kilogram Kelvin for aluminum, and 0.23 kJ per kilogram Kelvin for iron. This result showed significant deviation from the theoretical values, which is 0.385 kJ per kilogram Kelvin for copper, 0.887 kJ per kilogram Kelvin for aluminum, and 0.462 kJ per kilogram Kelvin for iron. The percentage errors is 13.6 for copper, 53.2% for aluminum, and 50.3% for iron respectively. The total entropy generated during the heat transfer was 0.0053 kJ per Kelvin for copper, 0.0018 kJ per Kelvin for aluminum, and 0.0027 kJ per Kelvin for iron. The positive entropy values indicates that the heat transfer process is irreversible, a characteristic of a real-life process. The metals underwent exothermic reactions as evidenced by their negative entropy changes, while the surrounding water experienced positive entropy changes. Errors in the experiment came from impurities in the metals, environment factors like airflow, and reading inaccuracies. Improving these conditions could lead to more accurate results.
Safety procedure. The first one is PPE, which is personal protective equipment. Ensure all group members wear appropriate PPE, including lab coats, safety glasses, and gloves throughout the experiment. The second one is metal block inspection. Before start experiment, inspect metal blocks for any impurities or rust. Clean them using distilled water, and if necessary, sandpaper to minimize impurities that could become volatile upon heating. The third one is fire safety. Ensure the availability of fire extinguishers and educate group members on the proper usage in case of a fire-related emergency. The last one is electrical safety. If applicable, ensure all electrical equipment such as the hot plate is in good condition, and emphasize safe handling to prevent electrical hazards.
Reference. This is the reference that we're using in this experiment.